So welcome back to this special topic on quantum computing and quantum machine learning. I wanted to give you some of the same messages which we went through last week. So we are going to use extensively GitHub in order to place all the teaching material, which means in turn that if you just do a Git clone, you can then actually save everything onto your laptops and use the teaching material as you want. Now, there are 3 textbooks which I try in a way to use and give some reading recommendations from. Some of them may be a little bit too much on the mathematical side. The one by Scherer contains a lot of the basic mathematics, which is of interest for us. And then the one by Robert Hunt is actually an interesting text because it contains many of the same things which I mention every week. But it's always linked up with a way you can write a program for this. So last time we went through some basic definitions. I'm going to repeat some of them. We looked at mathematical notation, we looked at Hilbert spaces and operators, and we looked at description of quantum systems and 1-qubit systems. And most likely what you saw is that essentially what we end up with is applied linear algebra to a very large extent. And this course will actually rotate around applied linear algebra. You will also find the slides. If you click on links like this one, you can choose the kind of format you want to use, whether you want to just look at the HTML file, or you want to look at the Jupyter notebooks, or if you just want to look at the PDF version of the slides. So I'm trying to update these slides as frequently as possible. You will also find, after every session which we've had, a video of the lecture. So that should give you a kind of a rough overview of what we've gone through. And then you will also find the handwritten notes. And these are basically the notes which we went through. Now, for this specific week, what we are going to continue with is also definition of tensor products and the definition of a computational basis, just a repetition of that. We are going to look at some simple Hamiltonians and other operators, and we're also going to look at quantum operations and the specific types of matrices, which many of you have seen before, like the Pauli matrices, which are matrices which we can actually reinterpret in terms of so-called quantum gates or operations on systems of qubits. But the important thing is us having defined a computational basis. So I'm going to repeat a little bit what we went through last time, and then we are going to dive into discussions of the topics for this week. And the thing which is of interest for us is also the discussion of these simple Hamiltonians, which we will use to define our first exercise. And this exercise will also function as our first stepping stone towards a larger project. And we're going to discuss that a little bit more in detail. So the slides which you will find contain sometimes a little bit more material than I will have time to cover, but feel free to read them together with the discussions which you will find in the textbook here. So this week is the first week when we have exercises. You probably also received an email about evaluation forms and also questions about what kind of topics you would like to discuss. So this is a course on quantum computing and quantum machine learning, which means that we will have to deal with these topics. And feel free, if you haven't answered the questionnaire, feel free to do that, because then we can decide upon what kind of evaluation form we want to do. Any questions so far about practicalities? If there are things which are unclear, things you would like to bring up, just let me know here. And then we will try to answer these as soon as possible. So just let me know in case there are questions or things which are unclear. But today I thought we could actually start with the first exercise set and start discussing how we can build up a major type of project where the first aim is actually to evaluate the eigen pairs, that means eigenvalues and eigenvectors, for a system, a very simple Hamiltonian system, but a system where we actually use methods from quantum computing to find the eigenpairs of a simpler Hamiltonian. Okay, so I'm going to switch over to the Jupyter notebook and just remind you quickly of things we went through last week. So if you now look at the Jupyter notebook here, what we went through last week, and you will typically find this, the summary from last week and plans for this week. So we went through the definition of a state vector, introduced inner products, we introduced the outer products and projection operators, and then we introduced also some tensor products and showed how to construct state vectors for multiple qubits. Now, today we are going to revisit these tensor products and link that with the computational basis again. So this will be partly a repetition from last week. I'm going to say something about quantum measurements, and then we are going to switch over to quantum operation and special matrices, simple Hamiltonians and other operators, and the first exercise set. Now, one thing which is very important, which we also discussed last time, is the definition of a computational basis. So this basis is a basis which we assume to be orthogonal and normalized, often shortened to orthonormalized basis. And this is normally written in terms of this acronym ONB. And in this particular case, we could think of us having one single particle, which is represented by two possible states, one which we call phi 0 and one which we call phi 1. And we can interpret these ones as, and this is what we're actually going to interpret them as, is a bit 0 and bit 1. And in this specific case, a possible basis is actually the one you see here, where we have two so-called vectors, 1, 0 and 0, 1 here. This could correspond to the spin degrees of freedom for what we in quantum mechanics would call spin half objects. And so this could be the spin up part and this could be the spin down part. And it's pretty straightforward to see that the overlap between these two states, 1 and 0, is exactly equal to 0. Just perform the operations. We also defined what we called the identity operator, which in this case is now the outer products of these two states. So we will encounter the outer products again and again, and that obviously becomes a matrix. So this is what we normally call the identity operator or the identity matrix. It's easy to see that I to the power of n is always equal to itself. And then we had in addition the projection operators. So this operator here actually projects out a component 0 if we have a linear superposition of these 0 and 1 states. And then we had the other operator Q here. And these two operators are so-called idempotent operators. You're going to encounter them a little bit later, and they are useful when we do many-body physics and we want to project out specific states. These two operators, they commute with each other, and P times Q are equal to 0. They also play, for those of you who have studied many-body physics, you probably encountered these operators since they are used to project out specific degrees of freedom. Now, one of the other things which we did last time was to define the superposition of states. And with this basis, you could now think of this basis phi 0 and phi 1, or just 0 and 1, as I will often use. We can think of that as a basis which is now a complete orthogonal and normalized basis. And with that, we can make a superposition and define a new state, which is given by a linear combination of these states with a given coefficient in front of it. And what we saw then is that these coefficients alpha are simply the projection of the state with 0 on this state psi, and the same with the coefficient beta. So they represent the overlaps between the computational basis states and a new state, which is a linear combination of the computational basis states. Now, I'm going to stress a little bit again and again this term computational basis. So the computational basis, the way we have defined it here, is a simplification. And if you look at a realistic system, you will have an infinity of such states. And normally when we are looking for candidates for making quantum computers, candidate systems, we're often looking at systems which exhibit two well-isolated states, which we can use as computational states for quantum computations. And what you see here is more an idealized system, but you could think that these states could represent the lowest lying states in a many-body system, where we now have singled out the lowest lying state and the second lowest lying state. And we use these in order to perform specific computations. In principle, everything we deal with are complicated many-particle systems, and we have to project out some effective degrees of freedom from that. We are coming back to these things. So the things which we went through last time was also the action of these operators, P, on this specific state psi. And we see that P, being a projection operator, projects out the specific component alpha. And furthermore, if we now look at the other component here, we also have a projection operator Q, which now projects out this specific component. And you can easily see that by doing the algebra yourself. Now, there's one very important quantity here, which we are coming back to, and we will come back to that again and again. And that's called the trace of a specific state. Right now, I'm just defining it. So we have this state psi, and if I calculate the trace of that one, this is now going to be given by the outer product. And in this specific case, this outer product is defined by the computational basis states. And you see now that this becomes a matrix. Now, since the computational basis is an orthogonal and normalized basis, then the trace of the matrix, which is the sum of the diagonal elements, has to be equal to 1, because we have defined that specific trace or that specific sum here to be equal to 1. So this is the normalization, and we are coming back a little bit later today to this, because we have simply defined now that these states are normalized. And these states are normalized because we are looking at specific unitary transformations of the states here. We are coming back to that. And we are assuming that this is normalized to 1. We are coming back to unitary transformations a little bit later. But this is actually an important quantity, which we are going to see again and again in this course here. So just pay attention to that, the definition of the density matrix, which is just defined as the outer product. And we have looked at the density matrix of this specific state psi. Now, the trace of such a matrix is actually given by the sum of the diagonal elements. So let's just look at some specific properties in addition to what is in the slides here. So I'm going to switch to the whiteboard. So let me do that. Now feel free to interrupt me in case you have questions here. Now, if we now look at the trace, which I said is a very important quantity. So we define the trace of a state, trace or of a density matrix. So we have defined the density matrix rho, and then we have a specific state here, which is a linear combination of the two computational basis states. And we have two computational basis states. So this state here is now a linear combination of 0 plus beta of 1, which when we write it out as a vector is nothing but alpha times beta. So when we then set up the density matrix here, what we are going to get then is that this density matrix is now given by alpha times the complex conjugate. We have alpha times beta complex conjugate, and then we have beta of alpha when we do the math here, and then we have beta times its complex conjugate. So that's a density matrix. And there is an interesting property here. If we act with this density matrix on this state 0, for instance, that's the same as alpha, alpha complex conjugate, alpha beta. Later, we are going to look at the density matrix in connection with the definitions of entropy, and then also a very important feature, which is just essential for doing quantum computing, which is entanglement. These are topics which we will discuss in more detail next week. So when we look at this operation here, what we get then is simply a projection out of a specific set of variables. So we're going to have beta times alpha complex conjugate. So the trace of the matrix, which we have defined as the sum of the diagonal matrix elements, is simply given by the sum from I equals 0 up to n minus 1. And then we have the diagonal matrix elements of that specific matrix. There are some properties of traces which I'm just going to state without proof. So if we take the trace of a constant, so C is a constant, and this is the same as C times the trace of the matrix. And I'm going to put the matrix in boldface, and C is just a plain constant. If I take the trace of two matrices, this is invariant and the change of the order of multiplications. So this is given by the trace of B times A. So this is another property. If we have tensor products, so suppose now we have performed the tensor product of two matrices. I'm going to remind you quickly of that. And the tensor products, now we have a matrix A, and we have a tensor product of the matrix A with a matrix B. This is actually, and I show this without proof, these are just the top quantities which we are going to need a little bit later. So this is also another important property here. And if we take the trace of this density matrix, quantum mechanical density matrix, we found that that was equal to, for that specific 2 by 2 case, times beta and beta complex conjugate. And since the state was normalized, this is equal to 1. So this is just a quick introduction to traces. And these are mathematical quantities which we are going to need. And together with the density matrix, these are ways by which we will try to describe what we mean by entanglement. Now, what I'm going to do now is to switch over to the slides again, because I wanted to remind you of some of the things which we discussed last week. So one of the other things which we discussed then was actually the tensor products of composite systems. So if we now have two general vectors, so we saw the vectors 0 and 1, you could now think of a general vector of length n, a vector x, and when I write this, use this bracket notation, what it means is that this is the same as a general vector. So if you see this boldface quantity, this is just in our notation here, we are going to use this bracket notation, and which simply means this general definition of a vector with two components. And then we would have the same for the vector y here. And if we do the tensor product of these, it's common to rewrite this just as xy here, instead of writing at that x tensor product with y. Last week, we discussed this in terms of general quantum mechanical single particle state, which had the spatial degrees of freedom, and then we took the tensor product of the spatial degrees of freedom, which live in their Hilbert space, and the tensor product with the spin degrees of freedom. Now, in this particular case, we obtain, since we have two vectors of length 2, we obtain a final vector of length 4. Now, one of the things which we're going to use a little bit more now is also the definition of a 2-qubit system. So you could now think of using your original qubit system or any system. So this is not limited to this kind of specific states. Now, these states could represent a discretization of integration points in, let's say, a diagonalization of an eigenvalue problem. These vectors here, which we have now, we are going to encode them as 0, 0, and then later, to obtain a compact notification, we are going to encode it as a 0. And similarly, we can now produce the different tensor products, which you just see here. And it's easy to see that this new basis also becomes an orthogonal basis, and it's also a normalized basis. So these are also some important properties of these tensor products. So if you have an original basis, which is orthogonal and normalized, the new basis is normalized and orthogonal. So you could rewrite them or relabel them. So you could have a code which makes a list of these specific states, and you could relabel this one as a 0, this one as a 1, this is a second state, no, third state actually, when you come from 0, and this will be the fourth state. And you can proceed in this way. So you could now take a 3 qubits, and this will be the tensor product between these states, these single qubit states, which form a computational basis. And now we would have a new basis, which now contains 3 qubits. If you look back at this could now define these 4 states here, 1, 0, 0, 0, 0, 1, 1, 0. They could actually define a new computational basis for 2 qubits. And we are coming back to this gradually here. But these are just definitions. And again, just to quickly remind you of some properties of measurements, and no, sorry, on tensor products of 2 matrices. You could now think of 2 by 2 matrices, and the tensor product then would simply translate into a 4 by 4 matrix when we have 2 by 2 matrices. I guess you probably have seen some of these definitions before. So if we do measurements, just to quickly remind you of that, then the probability of a measurement on a quantum system giving a certain result is determined by the weight of the relevant basis state in that specific state vector. So we have been considering this specific state, which you see here, and that means that a measurement can yield only one of these possibilities, either 0 and 1, and the probability of that specific measurement is then, if we now just follow the basic quantum mechanical rules, that would be alpha squared or beta squared. And we know that the sum of these two, since the new basis is also orthogonal and normalized, is always equal to 1. So after you've done the measurement, the state of the system is the state associated with the result of the measurement, whether that is 0 and 1. And we have also seen what happens when we operate with a state, this specific state, with the operators P and Q. So before we do that, what we are going to do now is to look at new types of operations which we can perform. And we are also going to look at operations which we are going to classify as unitary observations, or operations. And these unitary transformations or operations, they lead to what normally is called the quantum mechanical reversibility. And this has a very important property. So quantum mechanics is not like classical mechanics. Classical mechanics, if you can define all the initial values which define the equations of motions, the initial values, then you can predict the future motion of an object if you can specify all the initial conditions and eventually boundary conditions. So classical mechanics is something which we would say deterministic. And if you know the position in a future time, you can always go back to the initial conditions which you had. So we would say that classical mechanics is reversible and deterministic. Now, quantum mechanics is also reversible and deterministic, but deterministic from a probabilistic point of view. So there is a probabilistic determinism. So that's one of the main differences between quantum mechanics and classical mechanics. Now, feel free to ask questions, guys, because now, unless you don't have any questions, I'm now going to switch over to different operators and gates, and I'm going to use the whiteboard again. And some of the very, very important matrices which we're going to encounter are the Pauli matrices. And Pauli matrices are actually used to construct quantum mechanical gates with which we can operate on quantum mechanical Hamiltonian. We can also rewrite, for those of you who have taken a course in many-body physics, we can rewrite the operators in second quantization in terms of Pauli matrices. So the Pauli matrices, they play an extremely important role in quantum computing, because that's the way we are going to realize many of the operations we perform on specific states. I'm going to switch back to the whiteboard. So let's do that. So it's always good to switch back to the whiteboard because that slows down the pace a little bit. So let's just get that one down. So now we are entering a new topic, which we could just use a loose title on, and these are so-called quantum gates. And we can call them also quantum operators or operations. And it will become clear from the context what we mean by operations. Now, there's one very important thing, and that has to deal with unitarity. So when we look at the vector, suppose we have a vector phi here, that can be rewritten in terms of a unitary transformation multiplied with a previous vector. So that means that this vector phi, if we now use this computational basis as an example, that could be given by alpha of 0 plus beta times 1. And then the vector psi, that could be given by a gamma times 0 plus a delta times 1. And then we can now look at different components. So if you now think of this vector here, this vector is nothing but alpha times beta. And this vector here is nothing but gamma times delta. So I'm just writing it out in its appropriate linear algebra representation. So what we would have then, since this is a vector which has dimension 2, has the length 2, and it's given by a unitary transformation. So we could now define a matrix which now contains U00, U01, U10. So these are the coefficients of this unitary transformation matrix. And then we can now rewrite this new state as this matrix of U00, of U01, of U10, U11. And then we multiply this with alpha and beta. So what we see then when we write this out is that the component gamma of delta, gamma and delta here, is the same as U00 times alpha plus U01 times beta. And then I have a U10 times alpha plus a U11 times beta. So these will be the new components of the vectors. And you could think now of the component gamma and the component delta. Now, what is important for us now is that this matrix, U, is actually a unitary matrix. It has to be that. So which means that U of ij, when we look at the coefficients, so this is equal to the identity matrix, and this is the same as U dagger of U. So we know that this one is now the same as Uji. So the Hermitian conjugate is now given by the complex conjugation of the specific matrix element. Now, one other thing which is important for us now is that since this is a unitary matrix, and in case the coefficients are just real numbers, then we have an orthogonal matrix. This matrix here, the Hermitian conjugate, is equal to the inverse of the matrix. And that is where we get this reversibility. So if I know this transformation, then I know that when I act with U inverse on this state psi, then I get back to the previous state. So this is the reversibility. And basically, many of the quantum mechanical operations we're going to deal with, they are defined in terms of these matrices. So if you look at this operator, which we defined, this operator P, which was now defined in terms of this specific matrix, we see here that the determinant of this matrix P is actually equal to 0. So this matrix, even though P squared is equal to P, is a matrix which is idempotent. It's a projection matrix, but this is not a unitary matrix, which you can see because the determinant is equal to 0. So we cannot define the inverse of that matrix. And the same applies to Q. So the matrix Q, which we looked at, 0, 0, 0, 1, has also a determinant which is equal to 0. So these are examples of matrices which are not unitary. So if we are acting on a specific state, we cannot introduce the principle of reversibility. Now, furthermore, if we now have assumed that this basis state we start with, phi, is equal to, when we now perform the calculations, this is going to be equal to alpha squared plus beta. If we assume that that is normalized, what we will find then is that the new state, phi, which is going to be equal to phi times u Hermitian conjugate times u times phi. Since this one is equal to the identity matrix, we see that this one is also equal to 1. So that means that the length of the vectors are conserved under these unitary transformations. So this is something very important to keep in mind when we are dealing with the quantum computing. So we want to keep the reversibility, and that means that we have to deal with the unitary operations. So the Pauli matrices are examples of such matrices. So let's look at the Pauli matrices here and remind ourselves about their mathematical properties. So the Pauli matrix, sigma x, which you often will see written as just x, is a matrix which we are going to define as 0, 1, 0, 1, 0. So this is an entirely non-diagonal matrix. So it has zeros along the diagonal. What we see is that the inverse of the Pauli matrix, minus 1, is equal to 1 divided by the determinant of sigma x. And this is obviously multiplied with minus 1, 0, and 0. When I just use the simple rule for a 2x2 matrix for finding the inverse of that matrix. And we know that the determinant is just minus 1. It's pretty straightforward to see that. We have the two diagonal elements multiplied with each other, which gives 0, minus 1 times 1. So the determinant of sigma x is minus 1. And you will see that applies to all the Pauli matrices. And another thing which is important now is when you now look at the operations here. So if you take sigma minus 1 times sigma x, what we get then is simply 1, 0, 0, 1. It's easy to see that. There's another property which is also very interesting, and that is that sigma squared is actually equal to the identity matrix 0, 1. So this is something which we will utilize quite a lot. Now, the other matrices which are important are like the sigma y matrix, which I'm just going to state here. So the sigma y matrix is just 0, minus 1, 1i, and 0. So this is the imaginary component. And you will see again that the determinant of that matrix is the same as minus 1. And the inverse matrix is also easy to find. And sigma y squared has also the property that that's equal to the identity matrix. And finally, if we now take the sigma z matrix, that is given as 1, 0, 0, minus 1. And you see again that the determinant of sigma z is equal to minus 1. It's easy to find the inverse matrix. and the inverse matrix is actually equal to the matrix itself. And we see immediately also that sigma inverse in this case, when we plug in the values, it's equal to sigma. And it's easy to see that sigma squared is again equal to the identity matrix. So remember now the difference between the idempotent matrices, where P squared and Q squared were just equal to themselves. Now, these are important properties which we are going to utilize. Now, but before we move on, let's take a quick look at what happens when we now act on a specific state, this state phi, which is a linear combination of these computational basis states. So if we act with the sigma x on this specific state, what we will see then is that this is the same as 0, 1, 1, 0, and then I have this parameter alpha, and this is now acting on 1, 0, plus beta, acting on 0, 1, 1, 0, multiplied with that, and multiplied with 1, like that. And if you now look at what happens here, is that this gives us alpha times 0, 1, plus beta times 1, 0. So we've actually interchanged, and this is normally called a bit flip. Sometimes if we think of spin, you could think of this as a spin flip operator. So this gives us now, sorry, not like that, but in a more compact notation, which we have chosen. So this gives 1 plus beta times 0. If I act with just sigma x acting on 1, 0, if I take away this linear superposition of states, you see now that this gives us simply 0 and 1. So if we think of bit 0, and we associate that one, and this is basically the definition of qubits, with that specific quantum mechanical state, 1, 0, which we also have labeled as 0, then we can think of this as a bit flip. Or if you don't want to think of bits, you can think of, if these are spinors, which represent the spin degrees of freedom of a spin half object, then this would simply be associated with a spin flip operation. So you can think of this as a bit flip. And similarly, if you now take sigma x and you multiply that one with 0 and 1, which is the same as sigma x acting on 1, what you have then is that you have the state with 0. So the sigma x operator, or the matrix itself, is something which we can now represent in terms of a logical operation. So let us quickly remind ourselves, before we take a small break, of a classical NOT gate. So a classical NOT gate is a gate where you send in a bit, and then this bit gets transformed to a new one. So this will be the input bit, and this is the output. And the table looks like this. So we have the input values, and we have the output values. So you could think of sending in bit 0. If I send in bit 0, then I get bit 1. If I send in bit 1, I get bit 0. So this is a negation. So if you set up a table here, this is what we could have. So that means that we could now think of us setting up a quantum mechanical operation where we flip, for instance, the spin. Suppose we apply a magnetic field on a system of electrons, and these electrons are in the spin down state, and then by applying the magnetic field, we flip the spin. So this spin flipping could now be interpreted, since this is a quantum mechanical system, as a quantum gate operation. So these are normally called gates, So the quantum mechanical equivalent of that is the quantum mechanical NOT gates, which I just write as a Q naught or just NOT. And that's represented by the Pauli matrices given by sigma x acting on a specific state. So that is a bit flip operation, which now can be represented by the Pauli matrices. So this is extremely useful for us as we are moving on, and we're going to study more complicated systems. So you will see the definition of the classical NOT gate in terms of the sigma x matrices. Now, if you now operate with the other matrices, so if I take now the sigma z matrix, so what you will see then, if I take sigma z and act on this state phi, and this state phi was now defined in terms of this linear combination. So I have my state alpha multiplied with 1, 0, plus beta multiplied with 0, 1. If I do that, what we're going to see then is the following. So I will get a new state which has an alpha, but then I'm going to get 1, 0. But now I get a minus sign here of beta 0, 1. And I would rewrite this as an alpha. So nothing happened with the 0 bit, but then I change the sign. So this change of sign is something which we are going to later connect with something which is called phase changes. We are just anticipating the results. Now we are just stating what happens here. So this minus sign is something which we are going to interpret later in terms of so-called phase changes. And we are coming back to this. So in general, what we have now is a set of gates which are extremely useful for us in order to set up quantum computations. And the sigma x gate is a gate which we are going to identify in terms of the NOT gate. So the quantum mechanical NOT gate is represented by a spin flip. So I also wanted to remind you that we have some commutation relations between these matrices. And you may remember that sigma x and sigma y is now given by I of sigma z times a factor of 2 here, which is easy to show if you just put up do the algebra with the matrices here. Any questions so far? Anything which is unclear? Okay, so let me just also repeat a short note on what we normally call Hermitian operations. So, and then we conclude this first lecture. Short reminder on Hermitian operations. So if I have a scalar alpha and multiply that with a matrix, and I take the Hermitian conjugate, this is the same as the complex conjugate of this parameter. We assume that these are parameters which are complex. If I have two matrices, A times B, this is the same as the matrix B, Hermitian conjugate, times the matrix A. If I have a matrix A acting on a state phi, and I take the Hermitian conjugate of that one, this is the same as the state phi. That means that this becomes a row vector now. The previous one is a column vector. The next one is a row vector. And this is now multiplied with the Hermitian conjugate of the matrix. And similarly, if I have two matrices, A and B, so you could think of two sigma Z matrices, or sigma X and a sigma Z matrix, operating on a state, which is the way we are going to build up the quantum computing operations. So as I said, quantum computing is essentially just applied linear algebra here. And then this will be the same as phi. And then we have a B Hermitian conjugate and an A Hermitian conjugate. And again, remember now that this vector is actually a row vector now. Just keep that in mind. And finally, if I now define my outer product between two states, psi and phi, then what I have is that if this is now an operator, I take the Hermitian conjugate, this is the same as phi multiplied with psi. And I hope you can see the difference between my psi and phi's here. Okay, so I see there's a question in the chat here. Yeah, that's correct. So I'm using a little bit sloppy notation here. So normally it's called the adjoint operation, the Hermitian conjugate. So I'm a little bit sloppy with the language here. That's correct. So they also call adjoints. That's correct. So this is just sloppy language from my side. I'm sorry for that. So sometimes instead of saying the Hermitian adjoint, I normally say just the Hermitian conjugate or just the conjugate. And it should be clear from the context what this actually meant, since we are dealing with either scalars, vectors, matrices, or tensors. Now it fits to take a small break. So I'm going to stop the recording or pause. So before we move on into a discussion of specific Hamiltonians, which we can study, I just wanted to say something about the properties of the Pauli matrices, which are properties which are going to be very useful. So one of the things which we haven't mentioned is about rotations. So if we think of a rotation in the classical term, what we would have, if we now look at a system in 2 dimensions, so suppose we have a component x1 and we have a component x2. So these are the 2 axes which we choose. And then you could now think of having a vector, an original x vector. So this could be x here. And then we perform a rotation. And then we reach a new point here. So this rotation is now given by a new vector x prime. And we have a rotation theta here. So if we now think of the coordinates of these vectors, so x is now going to be given by x1 and x2, obviously, that specifies the vector x. And then we have the vector x prime, which is going to be given by x1 prime and x2 prime. So this is the way we would typically define these states. Now, since we now want to insist on this kind of quantum mechanical labeling, we are going to rewrite this as a vector x and this as a vector x in the Dirac bracket notation. So that means that if we now rewrite this in terms of a rotation matrix, we know that this can be written as a cosine theta multiplied with a minus sine theta. So this is a typical rotation, sine theta, and then I have a cosine theta. And it's easy to see that when you're rotating around an axis, that this is the appropriate mathematical way of doing that. And this vector, which you see here, is just a vector x. Now, the thing which is interesting for us now is that we could easily replace this with quantum mechanical operations or vectors. So we could think of having now a vector x, which goes over to the state psi, which is now given by alpha times 0 plus a beta times 1. So bit 0 and bit 1, as we've been calling them. And this is nothing but alpha and beta. So we could think of performing a rotation around an axis, which we haven't specified what actually means. So we could now obtain a new state, psi prime, which is given by this cosine theta minus sine theta, and then I have a sine theta and a cosine theta. multiplied with alpha and beta here. Now, one thing you should notice, now since cosine and sines are the matrix elements of this transformation, so this is something we would label as a matrix U here, we know that this U, and this is actually an orthogonal matrix, U of t is actually equal to this one, and that becomes equal to 1, and it's easy to see that. So this is also an example of an orthogonal / unitary matrix. And that will also define a reversible process. So if we now look at the operation on, suppose now alpha is equal to 1 and beta is equal to 0, then what we would get is that the state psi prime is nothing but alpha times cosine of theta multiplied with the state 0 plus beta times sine. Just a moment, this is actually not beta, but it's actually going to be given by alpha times sine theta, and this is multiplied with the state 1. So what we have constructed now is a state which is a linear combination of these parameters alpha and the angles cosine theta and sine theta. Now we can rewrite this in a more generic way, and we are coming back to that in connection with something which is called the block sphere. But now I'm just going to state it in more general terms. We can now think of a vector which is given by psi, a new vector psi, which is given by cosine and then theta half multiplied with the state 0 plus, and I'm coming back to what this means. So we're going to look at this a little bit later, not today, but I just wanted to state it because I want to define simply rotations around the X, Y, and Z axis. So one of the things which is useful then is to define a rotation matrix. And probably some of you have seen it, but we are coming back to this in connection with the block sphere. So define a rotation around the X, Y, and Z axis. And these are given respectively by the following mathematical operations. So I have a theta here, which is now given by e to the I of theta half times a sigma x. And the thing which is interesting for us now is actually the following. If we now look at the Taylor expansion of the exponential, what we are going to get is powers of sigma x and squared, sigma x to the power of 3, etc., etc. And this is something which we can actually rewrite as e of, sorry, not that one. Let me just rewrite it quickly. It's actually not so easy, difficult to see that. So this is equal to a cosine theta half multiplied with the identity matrix. Because if you write out the expansion of the Taylor expansion of the exponential, we will have terms which have odd powers of sigma x, and the odd power of sigma x is a sigma x, and the even powers of sigma x and sigma x squared is equal to the identity matrix. Then we will get at all the even terms, which we can recognize in terms of cosines, if you look at the Taylor expansion of cosines. And then we're going to get a minus I of sine of theta half multiplied by sigma x. So we can actually rewrite this mathematical operation, which is now a rotation around the x-axis by an angle theta. We can actually rewrite that in terms of the Pauli matrices and the cosines and sines. So this is something which we're also going to look at a little bit later in more detail. Now I'm just stating the expressions. And you will also see that this represents a unitary operation, because if you take the Hermitian adjoint of that Rx, you will see that that gives you the identity matrix. Similarly, you have on the y-axis of theta, you would have e to the I of theta half of sigma y. And similarly, you would have a rotation on the z-axis, theta, which is e of I of theta half of sigma x here. And it's easy to see that if you take e of I of theta and give an angle theta and multiply that with a matrix A, and this matrix has the property that A squared is equal to the identity matrix. This is an important property. You can actually rewrite this as a cosine of theta multiplied with I plus an I of sine theta multiplied with A. So the matrix is this matrix which you see here. This is something which we can, this Rx, if you look at that one, you can actually rewrite it in terms of a matrix. If we now are looking at a 2 by 2 matrix, now let me just bring it like this, of theta. This is something which we can rewrite as a cosine theta half, and then I have a minus I of sine of theta half. I have an I of minus I, no, sorry, plus I of sine theta half, and this is a cosine of theta half. And I can do the same thing with the Ry matrix and the Rc matrix. If I just write down the Rc matrix, for instance, Rc theta, this is something which we can rewrite in terms of this angle, theta half, 0, 0, and E of I of theta half. So these are operations which we will find useful in just a few moments. Not this week, but a little bit later. So I'm just mentioning these specific operations here. Now, there's another matrix, which is also a very important matrix, and that's called the Hadamard matrix. And this is normally written as an H. And this specific matrix has the following property, and it's given by 1 over square root of 2, and then I have a 1, 1, 1, minus 1. Now, this is also a matrix which we can rewrite or actually interpret in terms of specific operations on the system. The important thing here is that this matrix, when that, for instance, acts, or this operator, when it acts on a state, suppose it acts on the state 0, this is the same as 1 over square root of 2 of 1, 1, 1, minus 1, acting on 1, 0. And it's easy to see that this gives us a linear combination. So we started with a state which was in just one specific state, this state 0, but then we can construct a linear combination of the state 0 plus the state 1. So we've actually created a superposition. This is going to be a matrix or an operation which is going to be extremely useful. And the way you're going to see this is actually in terms of specific circuits which you can set up. So you could now think of us having a system where you feed in bit 0 and you operate with a Hadamard matrix. And then your system now, when it outputs, is going to be given in terms of a linear superposition between bit 0 and 1. So this is typically the way by which you would now depict many of these states here, or many of these operations. Sorry for that. Now, if I take now the operation on a state with bit 1. So what we have now, we have made a superposition of bit 0 and bit 1, and we started originally with bit 0. If I now act with bit 1 on this specific system, then what I'm ending up with is 1 over square root of 2 here. And you see that also if I square this 1 over square root of 2, it means that the bit 0 and the bit 1 have equal probability of 50%. And if I make a measurement then my system is going to collapse to one of these states with a 50% probability. If I do that, if I do this operation now on the state 0, 1, what we're going to see then is that we also get a superposition, but now we actually have a phase difference. So we have a -1 here. So that changes sign. And we are going to see the interpretations of these quantities a little bit later. Now, these matrices can actually operate on many qubits. So we are not limited to only operations on 1 qubit. And these Hadamard matrices are defined as follows. So Hadamard matrices, so let's just set it up. They have some interesting mathematical properties. So if I now take H1, this is just equal to 1, just a scalar. H2 then is given by 1, 1, 1, and -1. So this is the matrix we have been looking at. So that's a 2 by 2 matrix. And now we can generalize this to a matrix of dimensionality 2 to the power of k times 2 to the power of k. And this is going to be given by h along the diagonal of 2 to the power of k minus 1. And then I have h to the power of 2k minus 1. And then it's going to have an h to the 2 power of k minus 1 and minus of h of 2 to the power of k minus 1. And you see that when k is equal to 1, this is exactly what we have. So you can actually build these matrices to become larger and larger. The matrix is symmetric. It has trace 0. So that's another important property, which we will also use later. H2k is equal to 0. And you will see that the matrix is symmetric. And we see that because the non-diagonal matrix elements are the same. And it has also a very interesting property. If I do now h times h of t, this is actually a matrix which is orthogonal. It would then contain n, which is now the dimensionality of the matrix, multiplied with the identity matrix. And n is just simply 2 to the power of k here, which is the dimensionality, the number of rows or the number of columns of this specific matrix. And the determinant of the matrix is also pretty easy to calculate. So this matrix is a matrix which we are going to encounter again and again in this specific course here. Okay, so I'm going to go back a little bit to the slides. If you have any questions about some of these practicalities which we've gone through here and these definitions, please let me know. So in the first 2 weeks, we are running through several sets of definitions here. So I'm going to go back to the slides. And there is a topic which I actually wanted to discuss a little bit more in detail. So one of the things which I mentioned before we jump into the Hamiltonians is the fact that the unitarity plays a very important role when we are dealing with these types of operations. Another famous matrix is the so-called phase matrix. So when we deal with quantum mechanical operations, it's always a unitary transformation or an orthogonal transformation which acts on a given quantum mechanical state. And in our case, if you think of specific states, so this becomes a little bit important now for the discussions we're going to have in connection with the specific Hamiltonians we will look at. So the aim here, or the focus here, is not on algorithms for, let's say, factoring large numbers or for making secret codes, etc., etc. We are going to focus more on solving quantum mechanical problems with quantum computing algorithms. That's the main emphasis here. So you will see us now switching rather quickly over to quantum mechanical problems. So I'm going to mention topics like factoring, Shor's algorithm, and etc., but that will not be the main emphasis in this course. So, but typically what we have is a given state, psi here, which is now represented in terms of this unitary transformation. And these states phi, which you see, they're often chosen to be eigenstates of a specific part of the full Hamiltonian. As we mentioned last week, what is very handy to do in many body physics and in quantum mechanical problems is to define a basis which is orthogonal, normalized, and which can be seen as a solution of part of the Hamiltonian. And it's pretty common to single out a part of the Hamiltonian, which is a one-body Hamiltonian, where you have kinetic energy and an eventual external potential. And you can actually solve this problem either easily numerically, or you have nice analytical solutions. So often you will encounter quantum mechanical operators of the one-body type, like a kinetic energy plus a Coulomb interaction, or a kinetic energy plus a harmonic oscillator trap where the particles are confined to move within. And this is often a problem where we have even analytical solutions for this single particle basis. And we know that it's pretty easy to show that if this is an orthogonal basis, then this is also an orthogonal basis if this is a unitary transformation. And here is actually the proof of what we discussed before the break. So you can simply take now, and this is now translated in terms of vectors. We have assumed that vector Vj and vector Vi are parts of an orthogonal basis. And then we have an orthogonal or unitary transformation. And when we apply that one, we simply end up simply with this relation here, which simply tells us that length is conserved. So for our basis states, we could simply then set up this linear combination, and assuming that this is a unitary operation or unitary matrix, then we can actually show that this basis, if this one is orthogonal and normalized, then the new basis on the left-hand side is also orthogonal and normalized. So in principle, you should also pay attention to the fact that if this basis, which we are using, if this is a solution to a quantum mechanical problem like this, normally this would contain an infinity of basis states. But for practical calculations, we have always to make some kind of truncations. So what you will find here is a typical example, which you can run through if you want to. So I'm not going to discuss this because we discussed it a little bit before the break, and we actually went through these calculations where we related these two basis states, and then we found the unitary transformation, and then we can rewrite this in terms of a matrix times the vector here. And then if we have already assumed that this is normalized and orthogonal, then by these operations, we end up with this expression here. And since this is put to 1, then the nu also has to be equal to 1. So unitary transformations are rotations in state space, which preserve the length. That means the square root of the inner product of the state vector. And this becomes very important when we are dealing with the dynamics or the evolution of a quantum mechanical system. Now, the topic I wanted to end today's lecture with is actually a description of our first type of quantum mechanical systems and the first exercise. So I wanted to spend a little bit of time on that. So the typical quantum mechanical system, when we now use coordinates xi, this rij is normally the relative distance between two particles. That's the most common case, especially if we have energy conserving forces. They often depend on the relative distance between the particles. We would have an operator here, this H0, which contains kinetic energy and an eventual external field. And then we have an interaction between two particles, but we can also have more complicated interactions. And it's normal then, since this is an operator which acts on every single particle, it's actually normal to rewrite this in terms of a sum, so that we would have a many-body operator, but which is composed of just single particle operators. And these operators could, as I said, they could represent kinetic energy plus some kind of potential which confines the motion of the particles we are looking at. So these kind of parts of the Hamiltonians, this is a subset of the full Hamiltonian. Sometimes we can find analytical solutions to this. And we often use that as a computational basis in order to express the full basis in terms of these eigensolutions here. So there are many other properties. Normally the Hamiltonian is invariant under permutations. So these are important properties. And if you're dealing with fermions, one way by which you could approximate the solution to this problem here, this acting on a state. So if you have a basis, psi 0, as we mentioned, psi, which is an eigenbasis of this operator here, we can actually construct an ansatz for the wave function given in terms of these solutions. And this would then be an eigensolution of the many-body operator H0, which is then composed as a product of single particle state functions. So this could be our computational basis, and this becomes our computational basis for a many-body system. So these are just ways by which we can construct a many-particle state based on our computational basis here. So you can also show, and I'm not showing it here, that if this is an orthogonal and normalized basis, this many-body basis will also be defined in terms of a orthogonal and normalized basis. There is some matrix algebra here, which we are not going to look at. And the thing I wanted to dive into now is actually a system which is going to define the first exercise set. And this system here contains now one Hamiltonian, which we could think of as the non-interacting Hamiltonian, which has an analytical solution. And then we have the interaction, which we modulate with a strength parameter lambda here. So this lambda goes from 0 to 1. So if lambda is 0, there's only this part, which we assume we can solve analytically. And then we have for lambda equal to 1, we then have the full interacting Hamiltonian. So this could be 2 levels from a many-body system, or it could just be a 2-qubit system. Thereafter, we're going to extend it to a 4-level system. So some of you may have encountered this type of system. So you see now that when this operator here acts on this state, this has these states here, the basis states which you've chosen, 0 and 1, they are eigenstates of this H0. This is the assumption which we are making. And then what we can do next is actually to build up what is normally called the Hamiltonian matrix. So we will have a interaction matrix elements, which are then defined only by the non-diagonal elements. So we are assuming that these matrix elements contain non-diagonal elements and also some elements along the diagonal, which we have left unspecified. So let me try to explain what is going on here. So let's switch back to the whiteboard so that you see a little bit more clearly what is going on. So what we're going to have is, as I said, a 2-level system. And this 2-level system would now be thought of in the following way. So we have a 2-level system. So we have this state, and we have this state. And the exact solution for this is given by a psi 0 and a psi 1. So these 2 states are eigensolutions of the full Hamiltonian, which now contains this H0 plus this term lambda, H1, acting on psi 0. And this is now given by this eigenvalue, E0, multiplied with psi 0. And similarly, we have an H times a psi1, and this is equal to an H0 plus lambda of H1 of psi1, and this is the same as E1 times psi1. Now, we don't know these values. However, what we know is that we have a computational basis. So we have an H0, which now acts on this bit 0, or this 0 state, and that has an eigenvalue, epsilon 0, multiplied with the state 0. And similarly, we have an H0. So this can be a many-body state or just a state which consists of one particle. So we don't need to specify that. The only thing we can specify now is just the mathematics here. So the thing which we can do then is to assume now that psi 0 would be given by some coefficient alpha times 0, since we can always express that basis psi 0 in terms of our computational basis. So this defines our computational basis, comp basis. And this is a basis where we have the analytical solutions of. So the quantities which we have here, this quantity epsilon 0 and epsilon 1, they are known. These two quantities, they are actually unknown. And those are the quantities which we want to find by setting up a diagonalization problem. So this will be given by beta of 1. And similarly, I would have a psi 1, which is now given in terms of a gamma times 0 plus a delta times 1. And we could now rewrite these two vectors, which we have here, in terms of a unitary transformation, which is now the one which diagonalizes the basis. So if we now look at the Hamiltonian problem which we have, so if I take H of psi 1, and now I can multiply from the left with 0. If I do that, I can also do the same thing. I can do H times psi 1, and I can do the same with H of psi 0, and 1 of H times psi 0. Then I can set up a matrix now where the unknown coefficients are the coefficients alpha, beta, gamma, and delta. So what I could say now is that the general solution, or general vector psi, is now given by this transformation C acting on these vectors which we have, these vectors 0 and plus 1. So we would then have a multiply with the original basis, which I just write like an I here. Oh, sorry, I'm not going to write it like this. This was a step ahead here. Now, this is something which we can translate, for those of you who've seen this in quantum mechanics before. So we will translate this one in terms of a state 0 with H, and this contains a state 0. It's going to be a matrix, and then I have 1 of H times 0, and then I have, so this is 0 and 1. This is 1 of H and 0, and then I have 1 of H and 1. And then I have these unknown coefficients, which I get from diagonalizing. And this is given by C times the given energies. So this is and C's are now just vectors, which when we diagonalize will give us the linear combinations, which we have here. These parameters, alpha, beta, gamma, and delta, these are parameters which we will find when we diagonalize, and we find this coefficient C here. So this is basically the eigenvalue problem which we're going to set up, and we know that we can solve this analytically. And if we do that, so let's go back to the slides here. So I'm assuming that you've seen something similar before. So what we're going to assume now is that we know the specific values. So the matrix elements between the interaction and these given basis states is something which we can calculate. This is often the motivation behind us finding a specific basis. So if we can find a handy basis, sometimes we can even extract analytical expression for these integrals. These are integrals actually. But what it means is that we can translate our eigenvalue problem for these two states into a 2 by 2 matrix, where we have this lambda, which varies from 0 to 1. We have assumed that epsilon 0 is smaller than epsilon 1. And the only thing we need to do now is to set in values for x, and this x0 and x1. And in this specific case, what I've done is simply to set up a simple Python code where I actually run through this case. And the thing which is interesting now, and which I want you to analyze, is actually what happens when we increase the strength for the interaction. Actually here, you will see that everything is described by the computational basis state 0. Here, everything is described by the computational basis state 1. Then as you move, there is a level crossing here, where this state now, or this eigenstate, is dominated by the state 1, whereas this eigenstate is now dominated by the state 0. So one of the things I want you to do is actually to look at how these eigenvalue coefficients develop as you increase the strength for the interaction. Now, there's more to the picture than meets the eye here. So one of the reasons why I bring this up is that this is something which is going to be tightly interwoven with a discussion of entanglement. And when we have defined entanglement and something which is called a von Neumann entropy, we are then going to see that there are interpretations of entanglement which we can make due to this so-called avoided level crossing. So what happens here is that in terms of the computational basis, the states here change character. So the next case is actually us now making a new computational basis. So this is the next step in the exercise. And these specific Hamiltonians here, they are Hamiltonians which we will rewrite in terms of the Pauli matrices. And we are going to diagonalize them. And we are now going to look at a system with two qubits. And these qubits could be thought of as different systems, a system A and a system B. And it's normally to write this out in a little bit sloppy notation. So that means that qubit in system A is 0 in the 0 state, and the same for system B. And this is given by this specific state. Similarly, we would have the 1-0 state, the 0-1, and the 1-1 state. And we are going to think of these as our computational basis states of the non-interacting Hamiltonian. So that means that we know these specific values. So these are the computational basis states, and we can repeat the same exercise, the same Hamiltonian matrix, but now the interaction is going to be given by Pauli matrices. And that gives us a Hamiltonian matrix, which is going to look like this. And we can also, from that one, we can define, for instance, the density matrix for the first eigenstate, the one with the lowest energy. And you can show that this has to run like this. Now, what I'm giving you here is actually a program which sets up this Hamiltonian matrix with a choice of values for, you see, I have an hx and hc, and these epsilons, which I can fix as I want. And you can then define the Pauli X matrix, and you can now define the tensor product between two Pauli X matrices and two Pauli Z matrices. So I have a Pauli X and a Pauli Z matrix. And you see now that what I'm doing here is I'm setting up this part of the Hamiltonian, which is now given by the tensor product of sigma x times sigma x, which is the one we have here. So this is the way I define the Hamiltonian. These are 2 by 2 matrices. And by taking the tensor product, I get a 4 by 4 matrix, and the same here. So I want you to go through these details and convince yourself about the correctness of these equations here. And then you can then run through here as a function of this strength for the Hamiltonian, which we now define to take 40 values, and that runs from 0 to 1. So I have 40 values for this parameter lambda, and then I just fix this value 2 and 3. I fix also the values for these non-interacting energies, which are going to be this epsilon 0, 0, epsilon 1, 0, etc. And then you can then diagonalize and plot the eigenvalues. So what I'm doing here is simply to plot the eigenvalues. And in this case, I'm also having a so-called level crossing. And we are going to study the role of entanglement for this composite system. So this is coming, and we are going to spend some time on what this actually means and how we can understand entanglement in this specific system in terms of what's called the von Neumann entropy. So the first exercise which I wanted to point to consists now of some basic steps which we can reuse again and again. So the ideal here is that we want to find the eigenvalues of a given Hamiltonian using two algorithms, which we will describe later. One is the phase estimation algorithm, and then another one is the variational quantum eigensolver algorithm for finding eigenvalues. But the first practical thing is actually for you to set up a function which sets up the one qubit basis and then applies the various Pauli matrices to these basis states. So that means if you go up here again, it means us setting up these two qubit states, 0 and 1, and then play around with the Pauli matrices and convince yourself that what we went through in the lectures is actually what is happening. Then I want you to apply the Hadamard and phase gates to the same one qubit basis states, and also study the actions on these states. Now you have a library which is called Qiskit, where you can actually plug in everything. But I think it's more beneficial if we start writing these operations by scratch ourselves. Then I want you to rewrite the Hamiltonian of equation 7, which is this Hamiltonian, this one, in terms of Pauli matrices. And just to give you a hint, you can rewrite the non-diagonal part. This should actually be a lambda. It's not a C. This is a typo from my side. I need to correct that. But you can actually rewrite the non-diagonal part in terms of a sigma X matrix, and you can rewrite the diagonal part in terms of a sigma C matrix. So I want you to do that. And then when you've done that, you can then use the one qubit basis and you write a code which sets up the two qubit basis, study the behavior of these eigenstates for this Hamiltonian 7 as a function of the interaction strength, and convince yourself that there is a change of character. And then use the Hamiltonian for the two qubit example to find the eigenpairs as function of the interaction strength, and study the final eigenvectors as functions of the admixture of the original basis state. And that is extremely useful because later we are going to use that to define what we mean with the information entropy and link this with the concept of entanglement. Okay, so this is going to stop my lecture today. Now feel free to ask questions here about the first exercise set. I mean, we may not finish this this week, but the basic elements which you see here are elements which we are going to need when we later are going to set up a new model Hamiltonian, which will be defined in terms of Pauli matrices. So this will be the first exercise. I'm going to stop the recording here now.